Okay, in this video, we're going to analyze what happens during a collision. In a different video, we saw what happens if we're trying to analyze before and after a collision, but now we want to start and look at some of the nitty-gritty details of what's happening when these things are actually in contact. And in order to do this, we're going to explore demo number 3 from this week. And just a reminder, it was this kind of situation. Now, it looked a little bit different than the other ones, but the idea was the same. There was a track that had very low friction, and on the track there were two cars. We'll call them M2 and M1. And it was pointed out in the video that each of these cars had this little bumper on the front, this little, what is drawn in black here. And this bumper was really a sensor that allowed it to measure the force that was being exerted on that cart. So the one that's circled now would measure the force on cart M2, and this little bumper right here would measure the force on cart M1. All right, and the force is interesting to measure because really when these things are in contact, we know that they're pushing on each other in some way, shape, or form, and that's what we want to explore. Okay, and so this again is a picture of what was going on. It's right after the gray cart was moved, and it, was the hand was no longer touching it; it was just kind of zipping along. But before it came in contact with the green cart, before it came in contact with M2, and this force graph that is drawn on the right over here, what we want to look at is what was going on with that. Well, what would happen when these things were moving? They weren't touching, and so clearly there was no force on either bumper. And so it looked like, it'd just kind of be like a bunch of little data points, but they're all basically zero. And likewise for the gray. Okay? And so the force versus time graph was kind of look something like this. Great. But then what happened was these two came in contact. And so we've got a nice picture of this. And so I'm just going to copy this stuff. By copy it, I mean move it. And now we want to look at what happened when they actually came into contact. And so, again, this is just the same kind of picture. It's just making it clear that we're talking about during the collision. And the force versus time graph now, so this was kind of before they were in contact. And then once they were in contact, you saw something that kind of looked like this for one of the carts. And then you saw something that looked like this for the other cart. Okay? And I want to explore this a little bit. First off, let me just make it clear. This top one is the force on M2, and this bottom one is the force on M1. Okay, and that's what those graphs are displaying as a function of time. This time right here is the full, from here to there is the time that they are in contact. Let me make that a little better handwriting, in contact. Okay, and over here, this over here is kind of, and over here was kind of before and after they were touching. So it was basically zero because they were no longer touching. Now there was some interesting ringing that was an artifact of the experimental setup. What we're interested in are these kind of, the times when it was in contact, these kind of big up and down humps. Okay, first off, what do you notice when you actually looked at the graph in the video? Well, the first thing that hopefully you noticed is that the green graph, what I've drawn as the green graph and the gray graph, they look almost identical to each other, but they're mirror images. What this means is upwards is the positive force, downwards would be a negative value. The fact that they are the exact mirror opposites of each other, but one is positive and one is negative, it means that these forces are equal and opposite, right? And so again, these are the forces on the two carts. When they're in contact, Newton's third law tells us that those forces from M1 on M2 is equal and opposite to the force of M2 on M1. That is exactly what this chart or this plot is displaying. So this is more or less a verification of Newton's third law. Okay, and so that's not something that's new to this week. It's just kind of a side effect that I wanted to notice. All right, the next thing to notice is if you looked at the area under each of these curves. Now, I would encourage you to go and look at the area under the curves in the demo video, because what I've drawn here is just a sketch of it. It's not perfect. But if you look at the videos and the graph in the video, you would find that the area under the two curves looks almost exactly the same. So the area under the curves is the same value. Now, one is positive and one is negative. What this is showing us is that something has happened to cart M1, and it's a positive some positive amount of area under that curve. Whatever has happened to, that is what has happened to M2. The green is a positive amount. The exact corresponding negative amount has happened to M1. All right. M1 and M2 have the same mass. And if you noticed from demo number 2, not demo number 3, but demo number 2, when we talked about momentum conservation, what we saw was that the initial momentum from one cart was completely transferred to another cart. What we are seeing here is exactly the description of that for during the time these carts were in contact. So let me say that again. What this area under the curve is saying is the area under this curve is telling us how much momentum was given to cart M2 during this collision. And it was given to M2 because it's a positive value. This tells us how much momentum was taken away from cart M1. Taken away because it's a negative value. All right? And so if I were to just kind of re-sketch this, as a little note down here, this area under the curve is positive. This means that momentum was added to M2. All right, let me just erase this stuff. It's not needed anymore. And the gray curve was corresponded exactly. And the area under this is negative. And what this means is that momentum was taken from M1. And so because the areas are equal, that means the amount of momentum that was taken away from M1 is exactly the amount of momentum that was given to M2. All right? And so I guess all I'm trying to say is that the area, this is our first look, that the area under this curve is equal to the change in momentum. All right, so I want to explore that a little bit further. All right, and to do that, I've already got this sketch down here. Now, this is the force on M2. And notice that you remember it looked something like this green curve. So the change in momentum of M2 is equal to the area of this curve. All right? Now, so if I were to look at this and say the area of this curve, well, I guess it's all this stuff in here. finding the area under that curve is actually a bit challenging. And in order to do that, you really need calculus. So let me just make it clear that this is the sort of real area under the curve. We are not using calculus, and so we're going to have to approximate this. And we can do this really quite well. And to approximate this, what we're going to say is, okay, if I squint really, really hard, and I look at this curve, rather what I can call it is, let's say that it looks roughly like that. And this, there's some amount there and there that kind of makes up for the missed amount. And so this, the area under this curve, I can do this quite well. This is our approximate area under the curve. All right? And this I can do pretty easily. It's whatever this value is, this f, multiplied by this amount of time, delta t. All right? And this value, we can call it, this is the average force on the cart during the collision. So what we're going to say is that the approximate area under this curve, well, it's just the base, delta t, times the height, which is f average. This approximate area under the curve is the amount of momentum that was added to M2 during the collision. So let me summarize. Delta P of M2 is going to be the average force on M2 during the collision multiplied by the time of the collision. All right? This idea, the way that we've represented it here, this is the idea of impulse. Now, the way that your book writes this is it introduces this new variable j, and it's equal to f average times delta t. J is called the impulse, all right? And this is the average force during the collision. And this is the duration of the collision, the amount of time the things were in contact. All right? Impulse is a very commonly used term and variable. But really what you need to know is that the impulse is really just, the impulse is really just the change in momentum. Okay? The momentum afterwards minus the momentum initially. Okay, but again, this is the way the book writes it, and so we'll stick with this. All right? So, momentum will change before and after, right? And so if you're doing a problem where you're just looking at the before and the after picture, you want to use conservation of momentum to analyze it. If you're looking at a problem where you've got information about what's happening during the collision, that is when the things are in contact, then you want to use the impulse analysis. Okay, that's it.